Light waves. We use the phrase all the time, yet very rarely do we ever see any phenomenon that really exposes the wave nature of light. Now this demonstration is designed to do exactly that. It's really simple to set up, yet it's profoundly surprising. The first part of the experiment is a laser. I'm using green because the eye is most sensitive to green light, so it's really easy to see in a classroom. I'm using a laser pointer to make sure that it's eye safe, and I've arranged it so that if I twist it in the clamp, I can get the laser to come on and hold itself on. And now I'm going to shine the laser onto the second part of the experiment, that's the screen. You can see the path of the laser beam by just using a piece of paper. You can track the laser beam back towards the laser pointer by just moving it backwards and forwards, or slightly more dramatically, you can just use a mister to spray some mist in the way and give it that James Bond effect. Now the third part of the experiment is simply a thin piece of wire. Now this wire is about 100 microns in diameter. If I slide my finger up the wire, you should be able to see it quite clearly. Now the experiment consists of sliding the wire into the path of the laser beam. We then look on the screen to see what's happening. Now, before doing this, I like to ask people what they would expect to see on the screen. And normally, perfectly reasonably, they tell me they'd expect the spot to be obscured by the shadow of the wire. So if this is the spot, they'd expect the wire to move in front of it, something like that, so that on the screen we'd see a dark line down the center of the spot. But in fact, that's not what we see. Let's take a look at what actually happens. So I'm going to slide the wire across, and you need to be quite careful to get it. There we go. You should just be able to see here where the laser is shining over the wire. And on the screen, oh wow. If you look at the spot, you should be able to see that there's no dark line down it at all. It's still perfectly bright. But on either side of it, you can see bright and dark bands extending out many times the diameter of the wire or the laser beam. So the question is, how do we relate this pattern to the wave nature of light? Well, light waves travel from the laser over to the wire, and they diffract around each side of the wire. That is, they're bent to fill the space beyond and behind the wire, extending over to the screen. So in this region, we observe interference between the light waves that have come around one side of the wire and around the other. Where the waves are in phase, that is, where the crest of one wave matches the crest of a wave that's come around the other side of the wire, we observe constructive interference. And that's what leads to these bright regions on the screen. And it's what explains the absence of a shadow in the center. In this region, we've got constructive interference from light which has traveled around each side of the wire, because this point is exactly equidistant from either side of the wire. We also observe destructive interference. That's where the light traveling around one side of the wire interferes destructively with the light that's traveled around the other side of the wire. And that's what leads to the pattern we see on the screen. Now, it's easy to get lost in the maths and the geometry that explain this pattern, but that's not the point. The key point here is that it's impossible to understand this phenomenon without appreciating that light has a wave nature. And that is what makes this demonstration so important.